Hello, IB. We're looking at 22J, independent events. And to test for independence, we have to know that if you think about your probability tree, if you guys make your tree, you guys are looking at replacement or non-replacement. So independent events would not, the probability of one event would not affect the probability of another event. So they would not be dependent on one another. With replacement, we're saying if you do replace, then the events would be independent. Your denominator would stay the same. For example, if you're choosing marbles or flipping a coin, if you replace the marbles after each drawing, then each of those events, each of the drawings would be independent from each other. So now how do we actually prove this with our formulas and with some notation? You can say A and B are independent events if the occurrence of each one of them does not affect the probability of the other one from occurring. So for example, if you choose, if you're looking for the probability of A given B, it should not really be affected by B. So therefore, the probability of A given not B should be the same as whether B is there or not there. And that really is just the probability of A in general. We know that the formula for the probability of a given scenario, in our previous sections, we know that probability of A given B is the intersection over the probability of B. So if we have independent events where the intersection is just the probability of A multiplied by the probability of B over the probability of B, oops, excuse me, there we go, you're going to wind up just getting back the probability of A. So therefore, looking at this formula here, it just verifies that probability of A given B should also come out to just the probability of A. If we look at an example, when two coins are tossed, A is the event of getting two heads. So here is my possibility of getting two heads. So we've got, what is this, 6 out of 24, or 1/4. And when a die is rolled, event B is the event of getting 5 or 6. So we're looking here. That's 8 out of 24, or 2 out of 6. And then you guys wind up looking for, show that A and B are independent. Well, so they would not rely on each other. So we're looking for the intersection here. So first we test with the formula. Probability of A times probability of B would be 1/4 times 2, 6. We get 1/12. If you actually look at the two-way table, you're looking for the fact that the intersection, so we have getting a 5 or 6 or getting two heads, they overlap at these two specific points. So getting a 5 with two heads or getting a 6 with two heads. So that is 2 out of 24, or 1/12. So as these two match, you have just also proven independence, that you could just multiply the two and you get the intersection. And if you can just multiply the two and get the intersection, then yes, we know they're independent. So looking at this first example, if you're given that the probability of A is 1/2 and the probability of B is 1/3, and your union is P, how could we show that A and B are mutually exclusive and we try to find P to match that? So mutually exclusive just means there's no intersection. So we want that intersection to be 0. So mutual exclusivity is, we want the union to be P in this example. Probability of A is 1/2. Probability of B is 1/3, and we do not want to have an overlap. So can we force our P to work out for us? And yes, we can. 1/2, find our common denominator. So we will have 3, 6, and 2, 6, and we get an answer of 5, 6. For the second part of this question, we want to figure out what P is so that A and B are independent events. Well, for them to be independent, again, we want the intersection to be able to be found by just multiplying the two separate probabilities. So let's see, probability of A times probability of B, 1/2 times 1/3, comes out to be 1/6. Well, I want to find the union. I want to find P. So if I want to find P here, I'm going to substitute everything in, 1/2 plus 1/3 and minus the 1/6. 1/2 plus 1/3 we've already found is 5/6. So 5/6 minus 1/6 gives me 4/6 or 2/3. So P will have to be 2/3 for this example in order to make the two events independent, because this has to be true for independence. The intersection must be the product of the two probabilities. For this next example, you guys are given probability of A is 2/5. So we know for this entire circle, we've got 2/5 probability. Then the probability of B given A is 1/3. So out of A, what's also in B is 1/3. So we're going to go back to the formula that we were given here, saying that probability of A given B times probability of B. Well, the A's and B's are interchangeable, so we could also say probability of B given A, and then multiplied by probability of A. So probability of B given A is 1/3, and that's 1/3 of 2/5. So that intersection is going to wind up being 2/15. And I'm just filling in this Venn diagram so I can prepare myself to answer these two parts of the question. Probability of A is 2/5. So to find just what's in A, I'm going to take 2/5 minus 2/15. So I will have 6/15 minus 2/15, so 4/15. All right, and then for what's just in B, which is what I ultimately want to find, I can do a similar thought process here. So following the same setup, probability of B and not A, so just this part of B, not including the 2/15, would be the probability of B given not A, which you're told is 1/4, multiplied by the probability of not A. Well, if I know that the probability of A is 2/5, not being in A is 3/5. So then we get 3/20. All right, now that I've got all of this set up, I can go ahead and answer my two questions. So my probability of B is going to be the 2/15 plus the 3/20. So I want to put both of those together. And then for part B, my probability of intersecting A and not B, so A and not B, we've already actually identified as 4/15. All right, so we get 17/60 and 4/15. All right, guys, so pretty typical example for IB is asking you guys to prove independence or to test for independence. So R and S, are they actually independent events? Well, we know that for independent events, I would like the intersection of R and S to be the probability of R multiplied by the probability of S. If that's true, then we would have 0.4 multiplied by 0.5, and we would get 0.2. Now, I can't just say, yes, they're independent, because when you multiply them, you get 0.2, because you're going to get an answer when you multiply any of these events, whether they're independent or not. So what we actually need to test is the union of R and S going to equal the probability of R plus the probability of S minus the intersection of R and S as we found it as 0.2. You should be always given at least enough information to check for this. So I've been given 3 out of the 4 items, 0.7, 0.4, 0.5 minus this value here for the intersection. So if we have 0.9 minus an unknown value equaling 0.7, we know that this unknown value for the intersection will actually wind up being 0.2. All right? So therefore, because 0.2 is the intersection that we need to satisfy the rest of what's given to us, and it also is 0.2 when you multiply probability of R and S, therefore you can say R and S are independent events. Okay? So you guys will have to go through that process to prove independence for several of these questions. And they like to show up on the IB exams year after year. So you guys are probably already starting to work on your questions from this section, but go ahead and try number 2. That brings together the given formula and your intersection and union formula, and then you can use that information to actually conclude whether they are independent or not. All right, we will check this next time in class. Have a good night.